Yes. All right, awesome. So this is discussion 12, and we are looking at acid-base disturbances. So I think this discussion worksheet's pretty easy. I don't think there's anything too overwhelming on here. I'm going to teach y'all some tricks on how to work through these problems. And once you have those tricks down, this will be super simple compared to last week's discussion. So let's go ahead and hop on into it. So before we start on the actual discussion, I just wanted to do an overview of pH. So remember with pH, we have acidic and basic. And just a review, in case you've forgotten, acidic means a low pH. So we're going to be below like 7.34 or something. So as we get a lower pH, that means we're gaining more hydrogen ions, becoming more acidic. Basic is a higher pH, so that means we have less hydrogen ions. So hydrogen ions and pH are inverse of each other. So if we have a low pH, that means we have high hydrogen ions. If we have high pH, that means low hydrogen ions. So hydrogen ions are kind of what cause acidity, and a lack of hydrogen ions is what causes basic. I don't know, acidity and basicness, I don't know. But the average pH is about 7.35 to 7.45. I don't think you need to have that memorized, but I just wanted to put this on here for reference on the problems we're going to be working through today. All right. So this is something we'll see in lecture. Maybe we saw it today. I'm not sure. I did not make it to lecture today. I was not feeling well this morning. But these are going to be the primary kind of illnesses or disturbances that we're going to see that involve that acid-base balance. So first we have acidosis, and we have two types. We have respiratory acidosis and metabolic acidosis. So what acidosis means is the body is too acidic. We have a very low pH. We've accumulated a lot of hydrogen ions, and our body is in this acidic state. Whenever we talk specifically about metabolic acidosis, this could be caused by diabetes, type 1 diabetes. So people with type 1 diabetes, they have a problem, metabolizing glucose. And so they're going to use other sources like lipids and proteins, fats and proteins, to break down for energy into ATP. And the byproduct of that is going to be ketones and some hydrogen ions. So ketones cause acidity as well as hydrogen ions. So that would be an example of metabolic acidosis. Respiratory acidosis would be caused by like a really slow breathing rate. So if you're breathing really slowly, this is going to cause carbon dioxide to build up in the blood, causing the blood to become more acidic. So like an example where you would see this would be if someone, was losing a lot of blood, like if they were in a car accident or something, and they had a major laceration and they were bleeding out. Whenever you're losing a lot of blood, it's harder to transport oxygen. It's harder to absorb that oxygen, and you start to kind of breathe slower. So whenever that happens, we're not taking in enough oxygen, and we're building up carbon dioxide because we're not clearing it. And carbon dioxide will also cause acidity in the body. Next, we have alkalosis, meaning the body is too basic. Opposite of acidic, it's basic now. So we have our two types again, metabolic alkalosis and respiratory alkalosis. And metabolic alkalosis can be caused from like severe vomiting. So, if you are vomiting a lot, you're losing a lot of hydrogen ions. And whenever you're losing hydrogen, that makes the body more basic. Less hydrogen means more basic. Respiratory alkalosis would be caused by really fast breathing, which I don't know what happened to the rest of that sentence. But fast breathing leads to the lack of carbon dioxide buildup in the blood. So we don't have a lot of carbon dioxide because we're breathing in so much oxygen. We're breathing in way more oxygen than carbon dioxide. And so Whenever we don't have enough carbon dioxide in the blood, that will make it more basic. So these are kind of the four main acid-base disturbances that we're going to be looking at for this unit. So there's a trick on how to identify these acid-base disturbances, and it involves using this equation. However, this equation has a few too many parts that aren't necessary, and the important variables that we need to understand is this here. So the overall equation is you have carbon dioxide, you add water, that'll convert into H2CO3, which will convert to hydrogen and bicarb. However, what's important for you to know is the carbon dioxide variable, the hydrogen variable, and the bicarbonate variable. That should have an H in front of it. HCO3 is bicarbonate. And these will tell us whether we are too acidic or too basic, and whether it is a respiratory or metabolic issue. So this right here is something that you definitely are going to want to have down: CO2, H, and HCO3. So breaking this equation down, we have our CO2 equals hydrogen plus bicarbonate. What we see is with respiratory acidosis, we will have higher levels of CO2, higher levels of hydrogen, and higher levels of bicarb. And again, hydrogen ions and pH are inverse of each other. So make sure you know that relationship, because Dr. Chang could ask you about pH, or he could ask you about hydrogen ion accumulation. So just make sure you're using hydrogen ion, concentration as an indicator of pH. So, we have increased carbon dioxide, increased hydrogen ions, and increased bicarbonate. With respiratory alkalosis, we have decreased carbon dioxide, decreased hydrogen ions, which means an increase in pH, and decreased bicarb. Metabolic acidosis is kind of like respiratory acidosis, except it has a decrease in bicarb. And metabolic acidosis is just like respiratory alkalosis, except it has an increase in bicarb. So if you can get this down, which this isn't too hard to memorize, because both of the respiratory disturbances are all, in the same direction: carbon dioxide up, hydrogen up, bicarb up. And the metabolic, the trend follows, except the bicarbonate and hydrogen ions will be inverse. So if you can make that connection in your head, that with respiratory acidosis, and more specifically, honestly, if you can make that trend just between hydrogen and bicarb, this will be really useful and helpful in solving these problems. We'll see once we get into the worksheet on the next slide that the carbon dioxide isn't always a great indicator, because it's heavily affected by it changes quickly. So whenever you go into like metabolic acidosis, we'll see in a little bit that our body will compensate by increasing breathing or decreasing breathing rate. And that changes carbon dioxide levels in like a quick second. So we can't always use carbon dioxide to solve, but these hydrogen and bicarb ions, if you get this relationship with the respiratory diseases, they're the same direction. And with the metabolic, they're inverse, then solving the next problems will be really easy. So I definitely recommend kind of memorizing this right here. So now we're hopping into the actual worksheet. So this is just like a prettier version of what you have on your paper. And what we are given are some 3 normal values. We're given pH. Remember that pH, the indicator we use is hydrogen ions, so hydrogen ions. We're given concentration of bicarbonate, and we are given a partial pressure of carbon dioxide. So this is pretty much our equation. We have carbon dioxide equals hydrogen plus bicarb. Carbon dioxide equals hydrogen plus bicarb. But remember, when working through and trying to make a diagnosis, the main thing that we're going to want to analyze is pH and bicarb, or hydrogen ion concentration and bicarb concentration. The PCO2 again changes quickly, and we'll look more at why towards the end of the worksheet. But let's go ahead and hop on in. So A, what we have is a pH of 7.34. So what that means is we have an increase in hydrogen ions, because if our pH, our normal pH is 7.4, that's a decreased pH. And remember, a lower pH means more acidic. More acidic means more hydrogen ions. So that relationship is a little weird. pH, a lot of people want to think that like a higher pH means more acidic. It's the opposite. A higher pH means more basic. So lower pH, more acidic. So we have an increase in hydrogen ions for A, and we have a decreased bicarbonate concentration. You see our regular or normal bicarbonate concentration is 24, and I have no idea what MEQ over liters means, but it's less than 24. So that is that inverse relationship, an increase in hydrogen ions, a decrease in bicarb. And what that tells us is we're dealing with metabolic acidosis. So when working through problems like this, I would definitely have this previous chart memorized. So you can just write it out on your paper before you begin working through these problems. Just write out, respiratory acidosis. You can even abbreviate it RA, hydrogen up, bicarb down. Respiratory alkalosis, hydrogen down, all of that. So I definitely memorize this, because when you're working through these problems, it's super simple if you get those 4 minor relationships. B, we have a decreased concentration of hydrogen ions, because we have a higher pH. A higher pH means more basic. More basic means decreased hydrogen ions. So we have a decreased concentration of hydrogen ions and an increased concentration of bicarb. So again, we have that inverse relationship. And with inverse relationships, we know it's going to be a metabolic disease. So respiratory, they go in the same direction. Metabolic is inverse. So just try and memorize that, because it'll make it really easy. All right, and we know it's acidosis for the first one, because we have that increase in hydrogen ions, that decreased pH, and we know it's alkalosis for B, because we have a decreased pH, so it's more basic. All right, so C, we have a decrease in hydrogen ions, so it's more basic. You see the pH has increased, and we have a decreased, concentration of bicarb. So these two go together, they're not inverse. So that tells us it's a respiratory disorder. And if we have a decrease in hydrogen ions or an increase in pH, that means it's alkalosis. D, we have a decrease in hydrogen ions and a decrease in bicarbonate stores. So again, we have that equal relationship telling us that it's going to be a respiratory issue. However, this one, there's something to note about this one. It's that pH is super close to 7.4, which is our normal. However, that bicarb store had a very big decrease. So we had a huge decrease in that bicarbonate store. And whenever we have such a major decrease, we call that compensatory respiratory alkalosis. And our last question on this worksheet will go more in depth about the compensatory mechanisms. So I'm not going to explain it too much now, because this is kind of a hard example to explain it on, because we don't have the actual condition, or we have the diagnosis, but not what's going on with the person. But for now, just know if we have like a major decrease in one or the other, or a major increase or one in the other, it's going to be a compensatory disorder or diagnosis. And again, we'll look at why towards the end. And then lastly, for E, increased hydrogen ions, because we have a decreased pH, increased bicarb stores. If they're linear, that means a respiratory disorder. And because we have an increase in hydrogen ions, it means it's going to be acidosis. So respiratory acidosis. So again, you don't really trust the carbon dioxide. If you analyze the carbon dioxide, it would not match up to the chart that we did on the previous slide. And that's going to be due to this compensatory mechanism, which we'll hit that towards the end. But don't analyze carbon dioxide when working through these problems. All right, so now we're going to get into our case study. So now we have this man who develops this gastrointestinal illness, and he is dealing with nausea and vomiting. So anytime you see vomiting on one of these problems, that's going to tell us that we are what? Losing hydrogen ions. So vomiting means losing hydrogen ions. We're going to become more basic. After 24 hours of illness, he is sent back to the labs for tests. So here's our 24-hour lab test analysis. And then when the illness continues, he's sent back for a second collection, so at 60 hours. So what we're going to do is we're going to use this data to answer the following questions. So A is asking, what is his acid-base disorder? So respiratory or metabolic acidosis or alkalosis, and what is its origin? So when examining this data, there are a few things that we definitely don't need to worry about, like body weight, blood pressure, things like that. There are certain variables that are not important. However, one thing we've used throughout this whole worksheet is pH, carbon dioxide, and bicarb stores. So the first thing we want to note is that 7.5 is a kind of a high pH. So that means it's more basic, meaning loss of hydrogen ions. The 60-hour, it's still a pretty high pH, which means loss of hydrogen ions. When we look at the bicarb stores, we see that we have increased concentrations compared to those normal levels, which is like 24. So we have increased bicarb. So hopefully at this point you can make that relationship that, hey, these are not going in the same direction. They are inverse. And again, whenever we have an inverse relationship, that means it's going to be a metabolic disorder. So metabolic alkalosis. It's alkalosis because it is basic. We have a decrease in hydrogen ions, which means a decrease and acidity becomes more basic. And what is its origin? The origin is that loss of hydrogen ions due to the vomiting. So whenever you're vomiting, hydrogen ions are leaving your body, making it more basic. Just kind of add a little extra note of explanation on hydrogen ions, just an example in case you're kind of lost on like the pH and all that doesn't make sense. There's a very common misconception that whenever you're sore, it's due to a buildup of lactic acid, which is somewhat true. However, lactic acid is produced by an accumulation of hydrogen ions. So when you're really sore, or let's say you're walking up a lot of stairs and you start to feel the burn in your like quads, that's due to accumulating hydrogen ions. So the more hydrogen ions that accumulate in your body leads to soreness, aka acidity. Soreness and acidity are like the same thing. So whenever we have more, anytime I'm like starting to feel the burn when I'm working out, or if I wake up the next day and I'm really sore, what I say in my head as an exercise physiology student is, oh my gosh, I've accumulated so many hydrogen ions like in my muscle cells right now. Like I need to clear these because my cells are acidic due to this accumulation of hydrogen ions. And that's what leads to that burning feeling or that soreness. So just try and make that that connection between hydrogen ions. If there's a lot, that's acidic. A lot of people get really confused with pH, and I understand why. It took me a while to get it down. So just try and make those connections. All right, so B is asking us what has happened to the acid-base disturbance by 60 hours. So what we see is that pH from 24 hours to 60 hours has decreased slightly, just a little bit. So what we call this is compensation. So the plasma pH drops from 7.5 to 7.48. The body is trying to bring this person back to a regular pH, and the body is compensating. So the body is detecting at 24 hours, hey, our pH is pretty high, and it compensates by trying to decrease that pH. All right, C is what are the homeostatic compensations for this acid-base disturbance. And so this is what I was talking about earlier. Compensations with acid-base disturbances, there are two. First, we have respiratory compensation. So respiratory compensation is what our body does whenever the body becomes too basic. So when the body becomes too basic, which is what we're dealing with here due to the vomiting and loss of hydrogen ions, respiratory system will kick in by decreasing our breathing rate to try and keep more carbon dioxide in the blood. So you can see that here, from 24 hours to 60 hours, we have increased the amount of carbon dioxide in our blood. So that's respiratory compensation. We're trying to make the body more acidic, or we're not trying to make it more acidic, but we're trying to bring it back to normal from that basic level. The second type of compensation that we can see is renal compensation. So the kidneys, compensate as well. And what they'll do is they will try and keep more hydrogen. So they will excrete less hydrogen in the urine. They will reabsorb more hydrogen in the nephron. And therefore, we can try and take that basic condition of the body and bring it back, bring it back down, trying to make the body back to normal. So you can see that here, 7.5 to 7.6 and 60 hours means we have, this should say increased the hydrogen ions. Sorry, this arrow is wrong. Should be an increase in hydrogen ions because we're trying to keep, or I guess I was looking at pH when I wrote this. So it's never mind. Just think increase in hydrogen ions because we're trying to make the body a little more acidic to bring it back to normal. Real quick, I forgot my note on here, and I know it's important. Okay, yes. So what we see is that whenever we deal with metabolic disturbances, this will cause a rapid onset of respiration compensation, so respiratory compensation. However, this occurs in seconds, and that's why we can't really trust those carbon dioxide levels when determining metabolic or respiratory acidosis or alkalosis, because how rapidly that respiratory compensation comes on. So as soon as our body detects some type of pH issue, we will have this respiratory compensation in seconds. So that carbon dioxide level, unless you test it in seconds, which is very rare, it will not be accurate for a measure. What we also see is that renal compensation, deals with the loss of hydrogen in the urine, but this takes hours. Filtering the blood and the nephron is not a second process. It takes minutes to hours. So this is why we use pH and bicarb a lot more than we use carbon dioxide to analyze alkalosis and acidosis. However, with our metabolic problems, both of these can happen, but with respiratory problems, only renal compensation can happen, because if we're dealing with a respiratory disturbance, we have some type of disease in the lungs, and this is going to affect our breathing rate anyways. So we won't see respiratory compensation with respiratory alkalosis or acidosis. So make sure you know that both of these, 1 and 2, respiratory and renal compensation, can occur for metabolic problems, but for respiratory problems like respiratory alkalosis or acidosis, we're only going to see renal compensation. So kind of take note of that as well. Right, so lastly, oh my gosh, my last concept to teach is crazy. We are going to map the renal related compensations for this guy's decrease in blood pressure. So if we go back, we see that blood pressure has decreased from 110/70 to 80/40, quite a decrease. So what we see is that whenever we are dealing with metabolic alkalosis, we are going to excrete more bicarb, and we are going to reabsorb more hydrogen. So remember, metabolic is that inverse. Bicarb goes down, hydrogen goes up, and that's due to the hydrogen being reabsorbed into the bloodstream and the tubules of the nephron, and bicarb being secreted from the blood and then excreted in the urine. So When this happens, we're going to see this decrease in blood pressure because we're adding more hydrogen ions to the bloodstream. And we're going to go into this more in lecture, I believe, but I think whenever we add hydrogen ions to the bloodstream, it affects blood pressure somehow. But we have not learned that in lecture yet, so I don't know how to fully explain it. But I think hydrogen has some type of effect on the blood vessels, I think causing them to maybe dilate and relax. I thought I had a little note down here, but no. But yeah, that's all I have for y'all. Thank y'all again. Y'all have been great. Thank you so much for being patient with me. I was honestly so terrified coming to UT from Texas State to teach senior biology students. I wasn't even a biology major in undergrad. I was an exercise science major. So I never had to take a class as complex and detailed as this. So thank you all so much for being patient with me. Thank you all for being kind. I thought I was going to walk into a bunch of students who were going to be mad if I wasn't the perfect teacher. And not only have y'all been patient and kind, y'all have given me really kind feedback that has definitely stuck with me. I mean, I cannot be grateful enough. So I will always remember this semester. It caused me a lot of stress. There were many times where I was crying over the material in this course because not only did I have to learn it along with y'all, I had to learn how to teach it. So congratulations to y'all for making it through. This class was really hard. I mean, I'm a master's grad student, and this is way harder than any of the classes that I'm taking in grad school. So I just wanted to thank y'all, and I hope y'all have a great rest of the semester and a great Thanksgiving break. Relax and enjoy it. And yeah, that's all I have for y'all. So thank you so much. Bye, everyone. Thank you, Ari. Thank you, Rory. Oh, bye, y'all. I'm still recording.